Hey guys, this is Miss Gray, and you're here for chemistry once again. We're in Unit 7, which is all about reactions, and this is the best part of chemistry, after all. We get to see stuff happen. So today we're going to talk about 3 different kinds of reactions: acid-base, combustion, and redox. These are the ones that have the most dramatic changes. So this is the time when you get to light your teacher on fire. I know we're all looking forward to this, but calm down. So any reaction that involves an acid and a base is going to be producing water and a salt. That's how it neutralizes one another, because they're opposites. So an acid and a base, of course, is what we're looking at for acid-base reactions. Remember, acids always begin with hydrogen, right? Hydrogen ions. So like sulfuric acid is H2SO4. Wow, my blank got a little out of control. And then base is going to end with a hydroxide in its formula. OH minus is called hydroxide. So you already knew that from your experience in naming compounds, but I want to make sure that you see when we put an acid together with a base, look what we make. If I put H together with OH, it's going to turn into water. And so that's how it neutralizes. In fact, that's why water is neutral, because it has both an acid and a base, and so it neutralizes its own self. Let me move this writing out of the way. So acid-base reactions are simply a special type of double replacement reaction where we're going to trade ion pairs, and 2 compounds react to form 2 new compounds. So pay attention to where the ions are going. All right, check this out. First I have sulfuric acid, H2SO4. Here's my hydrogen that makes it acidic, and here's the OH that makes it a base. So the 2 cations are going to swap partners. You ready? I'm going to put the H with the OH, and I'm going to put the K with the SO4. Be careful how we do this though, because hydrogen has a +1 charge, and hydroxide has a -1 charge. So to make a compound with this, I just need one of each, right? HOH makes water. You can write this as H2O if you want to, but I'm going to keep it as HOH, so I see where they are. Now let's look at potassium. It has a +1 charge, and sulfate has a -2 charge. So I can't just put 1 to 1. It's going to take 2 positives to balance out the 2 negatives in sulfate, so I need K2SO4 for this formula. So when I put those together, sulfuric acid and potassium hydroxide, I'm going to end up with HOH, which is water, and potassium sulfate, which is a type of salt. Not the same kind of salt as what you sprinkle on your food and eat it. That's not what we mean by every single salt. A salt is simply an ionic compound made of a metal and a nonmetal. So ionic compounds are salts, and they always form as a result of acid-base interactions. So let's look at this whole reaction. We've already written this out. Now let's balance it. Because I had to have a 2 to 1 ratio for potassium, that means I have to have 2 potassium hydroxides to work with this 1 sulfate. So that's going to make 2 waters in the end. You've already learned to balance equations, so we'll spend more time on that later. Right now, let's make predictions about products. Here's a common one. Hydrochloric acid and sodium hydroxide combine where these 2 cations trade partners, right? So now I'm going to have sodium with chloride to make sodium chloride. And then hydrogen goes with hydroxide to make water. And so this should look familiar. Look, salt and water. That's the salt that you're used to, right? Sodium chloride is the stuff you put on your food. So when acids and bases react, we call them opposites. They're opposites of one another. One is always used to neutralize the other. But in the science lab, you would not treat an acid spill with another strong base, especially if it gets on you, because then you're just making the problem worse, right? We use weak acids to neutralize a strong base in a spill in the science lab, not strong acids or strong bases. Now let's look at combustion reactions. When we have a combustion reaction, basically, we have a compound reacting with oxygen. And oxygen is a diatomic element, so that's why its formula says O2. And it's always going to produce energy in the form of heat and light. So we can have a redox reaction with oxygen that makes iron turn into rust, but since it doesn't actually catch on fire, it's not called a combustion reaction. So they commonly involve what we call hydrocarbons. Guess what two elements are in a hydrocarbon? You got it, hydrogen and carbon make up hydrocarbons. And when we burn hydrocarbons, they're always going to make water and carbon dioxide. Isn't that crazy? When you burn something, you make water, but it's not like liquid water, like turning on the hose. It's water vapor and carbon dioxide, and those come out like as exhaust or smoke. Combustion will stop when either the oxygen supply is used up or when the fuel runs out, one or the other, whichever happens first. So let's look at some examples. These are the demonstrations we're going to do in class. So you're going to do some fire writing. You're going to write with fire using ethyl alcohol. And so the ethanol is going to react with water in this reaction. So we would want to balance this equation, right? Here's my formula for ethanol, C2H5OH plus O2. Don't forget the plus sign because we're combining it with oxygen. And I want to make sure that we understand combustion is not the same thing as heating. If we were adding heat to something, we put a little triangle there. But we're not. We're burning something. So if you don't know the difference between heating and burning, then come on over to my house and I'll burn some cookies for you. And then you'll see the difference between heating and burning, because I burn cookies a lot. I'm not very good at baking. So let's see the balanced equation. There we go. I needed 2 carbons and 2 carbons and 3 waters to give me 6 hydrogens altogether. And then we went back to fix the oxygen, and now everything's cool. Now we're going to see methane gas. This is the bubble solution. And so when we burned the methane bubbles, we were combining methane gas with oxygen. This is also one of the fires that we would do with a Bunsen burner, right? We send the methane gas through the Bunsen burner to light that on fire. But I like putting it in a soap bubble so we can pop it and have a big fireball in class. Don't tell my boss I said that. Okay, methanol or methyl alcohol is the whoosh bottle demonstration. Remember the rocket fuel? Yeah, when you light rocket fuel on fire, you got a big combustion reaction there. It releases a lot of energy very quickly because this is highly exothermic. And combustion reactions are called exothermic because they all release heat and light. And you know, when we do this in class, somebody's going to scream, so we'll all remember it. Now let's look at redox reactions. In this demonstration, we're either going to do the gummy bear death drop or the zinc pyrotechnics. But what you're going to see is electrons moving. Redox means the gain or loss of electrons, or it can mean adding oxygen to a compound. That was its initial quality, was adding oxygen, made it an oxidation reaction. But then chemists realized it's really about what the electrons are doing that makes something oxidation. So you can have a redox reaction that doesn't even involve oxygen anymore. So oxidation is the loss of electrons from one substance where the other substance is going to gain the electrons. So that's the part that is reduction. Both processes must occur at the same time because not only do we have to balance our equations for matter, we have the law of conservation of matter, we have to balance them by electrons too. So electrons have mass, they're part of matter too, they have to be balanced. So whatever you're gaining from one, you have to lose an equal amount from the other. Here's how to keep them straight. One way to remember is that Leo the lion says grr. Leo being the loss of electrons is oxidation, and the gain of electrons is reduction. So here's your Leo part, and here's the grr part. I know some of you think lions say roar, but they don't. They say grr. Another way to remember is oil rig. Oil rig stands for oxidation is loss, and reduction is gain. So whichever way works for you, that's how we keep track of oxidation or reduction. Now let's do some practice. Oh wait, not practice yet. I had to tell you about something else important. You see, any single replacement reaction, combination or synthesis, decomposition, and combustion, these are always redox reactions because they deal with transferring electrons. That's how those reactions take place. Double replacement reactions, including acid-base, they are never redox reactions because all they're doing is exchanging ions between different elements. They don't actually move electrons around. They just trade partners. Okay, now I think it's time for practice. Here we go. So for each element, we're going to classify the change of the underlined element as either oxidation, or I'm going to write an O, R for reduction, whoops, that word didn't stay together, and then N would be neither. So let's look at what happened to copper. Copper is the thing that's underlined here. Copper went from a 0 charge to a 2+ charge. So if we're going to gain a positive charge here, that means electrons have been lost. Remember, electrons are the thing that's negative, so the loss of electrons is oxidation. That's what Leo says about it. So number 1 is oxidation. Now I'm going to take my aluminum ion and add electrons to it. So this one's gaining electrons. Gain of electrons is reduction. Then my next one, I have CH4 and an arrow and O2. And so I must be missing some of my equation here. What I see right off the bat is that oxygen has been added to my carbon. So I'm going to call this one oxidation. Even though I don't have the complete picture of the equation, I'm going to make a guess that that's oxidation. My next one I have sodium hydroxide and hydrochloric acid. That's an acid-base reaction, and so that cannot be oxidation or reduction because that is double replacement. Gaining electrons, that's my GR part, so what's that? Gain of electrons is reduction. The oxidation number increases. So if this number up here, called the oxidation number, we call it the charge sometimes. If that's going up, then we're losing electrons, and the loss of electrons is oxidation. All right, now let's look at this one. I have a single replacement reaction where zinc is replacing hydrogen. So hydrogen in this compound is a +1 charge when it bonds with chlorine. And now in its elemental form, it's a 0. So I went from a +1 to a 0. That's going down. So if an oxidation number increases for oxidation, then the number decreasing must mean reduction. Hey, get it? Reduction goes down? That makes sense. Okay, look what I did. Magnesium plus oxygen, adding oxygen, oxidation. That's all there is to it. And so I'm going to ask you to identify whether something's being oxidized or reduced, but I'm not going to ask you to balance a complicated redox reaction. You just balance a normal reaction, and then we'll decide which thing is oxidized and which thing is reduced. That's it for the special types of reactions. I look forward to doing these demos with you in class because they're the fun ones. See you all soon.